Hi, this is the fourth video of the lecture series Digital Economy and Data Analytics. My name is Eiko van Vuren and today we're going to look at supervised learning for regression models. What we have done so far is that we have already been looking at, particular kind of prediction methods in order to, look at situations in which the outcome variable is going to be continuous. That is what we call the situation of regression in machine learning. But we should take into account that there are other, maybe more advanced methods that we can also use. And these are much related to the regression models that you already know of in econometrics. So in that sense, in order to understand the idea behind what we're going to do today, maybe it's best to actually ask ourselves the question how it actually works in econometrics and how we are essentially going to look at that at the moment that we're going to think more in terms of, a machine learner, a data scientist. So therefore, let's start actually with a very simple and practical example. So suppose that we have a data set with an outcome variable yi and a large set of features that we are going to have xi, where I actually runs from n1 to n, and we are going to assume that they are going to be iid to keep things as simple as possible. This is of course a setup that you have seen many times before already during your bachelor, and in econometrics we typically specify the so-called true model, and that is a situation in which we assume that on the left hand side we have a yi, and on the right hand side we have xi times beta plus ui, where, we're not always doing that, but at least in this most simple setup, we are going to assume that ui and xi, they're uncorrelated to each other. So therefore we simply assume that, the mean of ui conditional on xi equal to x is equal to 0. So these are the assumptions that we have made so far. And the important thing to realize is that in econometrics is that we typically assume that, this is the true model in the sense that we already know the axis that we actually have to include into this particular model, usually called, of course, the regressors. We typically assume in econometrics that, in fact, we do already know which regressors we should actually include into our analysis. All the econometrics that actually comes after that, like inference, looking at, say, for example, the standard deviations of this beta that we have over here, but also whether this beta is consistent or not. All that actually assumes that we actually do know what is included into this set of regressors that we have over here. But still an important question, and a question that you must have seen before, is of course what happens in the case that we are going to leave out one of the regressors in this xi that we have over here. So if we are going to, in terms of machine learning, if you're going to leave out one of the features, say this xsi that we have over here. So we simply going to do a regression based on this model that we have over here, but we are going to leave out one of the, one of the features, say this s feature that we have over here. We know that this could be problematic, but we also know that this is only going to be problematic in the sense that we are going to get inconsistent, biased and inconsistent estimators in the case that two conditions must be met. The first condition is a very trivial one, and that is that beta s, of course, must be unequal to 0. That's a trivial one, of course, because of the fact that if beta s would not have been equal to, if beta s would have been equal to 0, then at that moment in time, of course, this could be the true model over here, but of course, excluding that particular regressor, that particular feature that we've over here, would still be exactly the same model because of the fact that, then we just take out something which was multiplied by 0 anyways. So we should take into account that in that particular situation, it is very clear that if beta s is equal to 0, then nothing actually happens if we actually take out the particular regressor or the particular feature that we have over here. But we should take into account that there is another requirement that we actually need in order to have that something bad is going to occur to us. And that is that xi or xsi is going to be correlated with some of the other features. So even in the case that we have a situation in which beta, the beta s that we have over here, the beta s that we have over there, is not equal to 0, but still the xs, a particular feature that we're going to look at, is completely uncorrelated to any of the other features, then still at the moment that we're going to, incorrectly run a regression where we are not going to include the S feature that we've over here, then actually things are still going to be fine. And we do actually know that in that particular situation, it may be better to run a regression without, say, that particular feature. And the reason behind that is because of the fact that, then actually could have a higher efficiency. To conclude, at the moment that these two requirements are going to be correct, if indeed that beta s is not equal to 0, and if xs is going to be correlated with some of the other features, then of course it's always better not to exclude the particular regressor that we have, because of the fact that then at that moment in time we're going to get biased and inconsistent estimators. And at the moment that this is not going to be the case, so if, for example, beta is going to be, the beta s is not going to be equal to 0, and in the case that, xs is going to be uncorrelated with the say, any of the other x's, then it only makes sense to include, in fact, the particular feature if the correlation between yi and xsi is strong. That is to say that at the moment that we are going to have a t-value which is relatively large. Usually we say larger than 2, but at least we have to say that the t-value must be relatively large in order to make sense, in order to include that particular feature. Otherwise, it's always better to exclude the feature that we have at hand because of efficiency. Now the question that arises, how does this actually work in a learning context? Well, in a learning context, we should take into account that many of the things that I have said at the previous slide, they are not that relevant anymore. We are not that much interested in consistency or unbiasedness. We might even not be that much interested in efficiency. The only thing that we're really interested in is the predictive power of the regression. We simply want to have a regression that is as good as possible. So hence what we could do is that we are going to include all our features. So that means all the features, not only the features that were maybe included in this true model over here, but we're going to include any kind of features that we can think of that we essentially have in our data set. And then what we're going to do is that we're going to, not only include those features itself, but we might even try to include the cross terms, so interrelate them with each other of these particular features. We might use also higher order terms with respect to those features, so not just x, but also x squared, x to the power 3, x to the power 4, and interrelate them with each other, as already said. And then what we can do is that we can then try to find the best candidate for a potential learner gx that we have over here. However, we do already know that just including as much as possible will generally give a good fit on the training sample, but will just usually the risk then will not be the lowest. We should take into account that, of course, including more and more say regressors actually is going to help us in terms of getting a better fit on the training sample, but in the end the theoretical risk, we already know that, is not going to be the lowest, because remember this example with respect to k nearest neighbors, where we also have seen that taking the k equal to 1 is usually not the best thing to do. Even though it gives us the best fit with respect to the training sample, it's not going to give us the lowest potential risk. So in that sense, the question that arises what to do in this case. Well, before I'm going to say something about that, take into account that we already know this actually from the past, from other courses that we have taken in econometrics, because of the fact that we do already know that at the moment that we include more and more variables into our regression, then we do already know that that actually is going to improve the R squared. That implies that, say, we are going to get a higher value with respect to the R squared at the moment that we're going to include more and more regressors. But we should take into account that at the moment that we are going to get only a slight increase with respect to the R squared, that might already indicate that it might not always be a good idea to include that particular feature. And the reason behind that is, of course, because of the fact that then at that moment in time, we are going to increase the variance by quite a lot. So that's a thing that we have already seen in other, say, courses with respect to econometrics. But now coming back, how does it actually work in a learning context? Well, what we could do in this particular situation is that we're going to look at a very, well, potentially very flexible specification, including, say, as we did over here, including, say, many features, including higher order terms, and even its interactions. But what we then are going to do is that we are going to run all the potential regressions that we can actually do with respect to those features and higher order terms, as well as the interactions. So what we're going to do is just not use one particular regression, but we are going to use all the potential regressions that we can actually do with respect to the features that we are going to include. And then what we're going to do is that based on that, we're going to do either we are going to use a validation data set, or we're going to use cross-validation in order to choose the best performing model. Well, this is a very good idea. However, we should realize that that actually doesn't work in this particular context, at least not in many practical situations. In order to understand that, maybe the best thing to do is to look at a very simple example. Suppose that we have a training sample of, say, 1 million observations. Well, you should realize that this million that we have over here is not that important. Actually, most of the problems that we are going to have over here also even arises at the moment that we have many fewer observations, say only 100,000 or even only 10,000 observations. But the more important thing is that we are going to assume that we have only 50 potential features. That is not that much in a learning context, because of the fact that in learning context we usually have many more features, as I already said. For example, at the moment that we, would like to do things as, face recognition, then typically it's the case that, we are going to be in the millions of different features. But in this particular situation, we are only going to assume that we have 50 potential features. Then the question, of course, arises, how many potential regression models can we actually have based on 50 potential features? Well, that's not that difficult to calculate, because of the fact that you should realize that at the moment that you have a particular feature, then you can simply include that feature or not. So that implies that if I only have one particular feature, then I can, run two regressions. One regression in which I do not include that feature, so I only have a constant. That's a trivial regression, of course. And another one in which I'm going to include that particular feature. Well, it's not that difficult to understand then that at the moment that I have, two different features, then at that moment in time I can run 4 different regressions. One not including any of the regressors, one in which I include both features, and then we still have 2 additional ones, one in which I include the first feature but not the second one, and the other way around, of course, one in which I do not include the first feature but I include the second feature. That implies that more in particular, at the moment that I have 50 different features, then I can run 2 to the power 50 different potential regressions, and that will give me 10 to the power 15, more or less 10 to the power 15 potential regression models. Question, of course, arises, how many regressions do we then have to run? Well, take into account as well that what we have here is that we would like to do cross-validation. So, let's be, in this case, a little bit enthusiastic, maybe a little bit too enthusiastic, and use leave one out cross-validation. Then at that moment in time, what we have to do is that for any kind of potential regression that we have over here, in order to calculate the cross-validation risk, we have to do 1 million regressions, which implies that we are going to get the number of regressions that we get in total is 10 to the power 15 multiplied by 1 million, which in the end will give us 10 to the power 21 different regressions. Question arises, how much time is that going to take us? Well, let's suppose that doing a regression, of course, with 1 million observations, well, doesn't take that much time anymore, even, or especially if the number of features that we have is only 50. So, and many of them, they actually don't even include all of these 50 different features. So therefore you should realize that doing just one regression, of course, doesn't take that much time. But how much time does it take to do, for example, that many regressions that we have over here? Well, let's assume that we can do 1 billion different regressions in 1 second. I would be surprised if any kind of simple computer nowadays would be able to do this kind of thing. But if you have a cluster, then maybe it would be possible to do 1 billion regressions, 1 billion of these kind of regressions that we have over here per second. Then it will still take us 32,000 years in order to do this whole exercise that we have over here. That is much too long, of course. So therefore it would be good to obtain some methods that automatically select a subset of our regresses. And these methods are generally called regularization, as they try to reduce the number of regresses in the model. In order to get the general idea behind regularization, let's go back to the linear regression model. Remember that we had this model that we have over here, where we have at the left hand side yi, and the right hand side we have xi times beta plus ui. And we are going to assume that we have p features in total. Well, these could be all kinds of characteristics related to this observation I that we have over here. But this could also be, say, higher order terms of those characteristics, or even interrelationships between the different characteristics that we have. But we are going to assume that in total we are going to have p features. Well, one thing that we could do is to run all the different regressions that we have with respect to these p features that we have over here, but we have already seen on previous slide that that is actually not feasible. So therefore what we could do is to restrict ourselves to a, say, certain subset of, say, the potential regressions that we could actually do. One thing we could do is that we could restrict ourselves with respect to the number of features that we're going to be selected in this general xi that we have over here, to be no larger than alpha smaller or equal to p. So that implies that we're not going to include all the different, potential features that we could actually include in this xi that we have over here, but instead what we're going to do is we're only going to include alpha of them, where alpha, of course, is going to be a number, a integer number, of course, which means that it's going to be either 1, 2, 3, 4, 5, etc. Well, it can, of course, not be larger than p itself, because of the fact that we cannot include more features into this xi that is over here, more than the total features that we in fact have in our analysis. So that is the idea behind this. What we usually do is that we always are going to include a constant into regression. That's a thing that you already know from standard regression analysis in econometrics, that it doesn't make that much sense to run a regression without a constant. So therefore, what we typically going to do is that we do not count the constant in this alpha that we've over here, which implies that, for example, at the moment that we're going to have alpha equal to 1, that means that we are going to run a regression of yi on a constant and one additional feature. Alpha equal to 2 means that we are going to have a regression of yi on a constant and 2 different features, etc. And this implies, of course, that for a given level of alpha, we can simply run all the potential regressions that we have and choose the one with the lowest risk in a validation sample. So then we're going to get the lowest validation risk, and that particular regression that we're going to choose with respect to the alpha that we're going to choose. Well, an alternative what we could do is that we could also use cross-validation at the moment that we are going to just have, say, 2 different samples, only the training sample and the test sample, as we have explained in the previous video. So for example, at the moment that alpha then is equal to 1, then what we could do is that we can run then p univariate regressions of the features and choose the one with the lowest cross-validation risk. Because take into account that if alpha is equal to 1, well then it is indeed the case that we can only run p univariate regressions, because of the fact that then what we can do is that we can first of all run a regression of yi on a constant and the first feature that we have. Then we can run a regression of yi on a constant on the second feature that we have. We can also run, of course, a regression of yi on the constant and a third feature that we have, etc. And then what we can do is, after running all those different regressions, then we can choose the regression that in fact has the lowest cross-validation risk, or of course the lowest validation risk at the moment that we're going to use a validation sample. Now it's customary to always start with alpha equal to 1, and then after that to increment alpha every time by 1 and stop as soon as the cross-validation risk starts to increase. What we typically are going to see is that at the moment that we are going to start with alpha equal to 1, that then the cross-validation risk is typically quite large still. So even the, say, best regression that we're going to have will still have essentially a relatively high cross-validation risk. That is not that surprising, simply because of the fact that you only use one feature apart from the constant. So then you would also not expect the cross-validation risk to be extremely low. You would not be able to predict so well with just one particular feature. However, at the moment that we're going to go from alpha is 1 to alpha is 2, then we do of course see that the cross-validation risk will actually drop quite a lot. And that will probably also still be the case if we go from 2 to 3 and maybe also from 3 to 4. And that implies that we will actually, by incrementing alpha all the time by 1, will reduce with respect to the cross-validation risk. However, at a particular moment in time, if we increment alpha further and further, then at a particular moment in time we will see that the cross-validation risk will not decrease that much anymore. And it might even be the case that at a particular moment in time the cross-validation risk is going to start to increase again. But we should realize that then actually we have already found the potentially best regression, because this is actually quite comparable to what we already had at the moment that we were looking at k nearest neighbors. Remember there also that at the moment that we start with k equal to 1, then the cross-validation risk is actually quite high. Then at the moment that we go to k equal to 2, then it is already somewhat lower, and at the moment that we go on and on, we are going to increment k more and more. Well, we are going to get lower and lower values with respect to the cross-validation risk, but at a particular moment in time it's going to increase again. Well, we should realize that that also happens at the moment that we're going to increment alpha all the time, and do that with these regressions that we are able to run. And at the moment that we are going to see that the cross-validation risk again is going to increase, well, maybe you shouldn't do that immediately if you see that it goes one time a little bit up, because of the fact that that might be by coincidence. But if it really increases structurally by incrementing the alphas, well then at that moment in time you do already know that if you increment the alphas even more, well then the cross-validation risk will be even larger. And that implies that you don't have to run all those additional regressions anymore, because of the fact that you do already have the best regression. That actually increases the, at least it decreases quite the amount of regressions that you have to run. You no longer have to run all the potential regressions. You only have to run it up to the moment that you actually find essentially the regression that has the alpha which the cross-validation risk is going to be lowest. Then you do already have the best regression. This method actually has a special name because of the fact that it's called best subset selection. Take into account that even though this will generally be much faster than what we have seen so far, at the moment that you just run randomly all the potential regressions, but still take into account that this method can still be very computer intensive, especially when it's found that the optimal alpha is large. Question of course arises, how many regressions can you actually run for a particular value of alpha? Well, that's equal to, well, for that we can use these factorials that we have over here. It's equal to the factorial of p divided by alpha, the factorial of alpha, and p minus alpha. This is usually the combinations that you have. And take into account that, well, at the moment that, for example, alpha is equal to 10 and p is equal to 50, then we still have to run 10 billion regressions. That's of course much less than what we have seen on the previous slides, but take into account that that still is quite a lot of regressions, and take into account that if I find out that alpha is equal to 10, probably will not give me or generate me yet the optimal alpha, in the sense that, well, probably we still see cross-validation risk to go down quite a lot. Then I also have to investigate alpha equal to 11, and that will even give me more regressions for alpha equal to 11. So it's a little bit difficult to say how much time we are going to, to save with respect to this method of best subset selection, but take into account that it can still be very computer intensive. Therefore, there are also other methods developed in order to, well, be even faster. And an alternative method that has been used is so-called forward selection. Well, with forward selection, someone keeps the optimal feature set from the previous step. And that's actually different from what we have seen in best subset selection, because of the fact that we should realize that with best subset selection, what we're going to do is that we start with alpha equal to 1, well, and then after alpha equal to 1, we are going to go on with alpha equal to 2. But that means, of course, that we have to run all the different regressions, and it implies that we are not going to use the information that we already had from alpha equal to 1. So, for example, suppose that we find out that a particular feature is actually best to include at the moment that alpha is equal to 1, then we're going to forget about that feature in a sense, and we're going to take into account that actually for the second step, it could be possible that, say, other features are going to be included, not just that feature that we have. That is not what we're going to do at the moment that we're going to use forward selection, because of the fact that at the moment that we do forward selection, then if alpha is equal to 1, well, then we haven't included anything yet. So then at that moment in time, we do exactly the same as with respect to best subset selection. But then if alpha is equal to 2, we keep the, say, feature that we already know from alpha equal to 1 to be generating the, say, best regression, and then we actually only ask ourselves the question which additional, say, feature we need to include at the moment that alpha becomes equal to 2. So that implies that at that moment in time, the number of potential regressions that you can actually get is going to be much less, because of the fact that take into account that if alpha is equal to 1, then we can run p different regressions. If we then are going to assume that if alpha is equal to 2, that this feature that we have chosen for alpha equal to 1 is still going to be in the, say, optimal set at the moment that alpha becomes equal to 2, well, then the only thing we need to do is among the p minus 1 remaining features, we only have to choose the one that will give us the best regression. So that implies that now in this particular situation, well, you only have to run at most p regressions at a time, and actually at the moment that alpha is increasing, it becomes less and less and less, because of the fact that, well, at the moment that, for example, the number of features is equal to 50, then if alpha is equal to 1, you only have to run 50 regressions. But if alpha is equal to 2, then it's going to be 49. Alpha equal to 3, it's going to be 48, etc. So that implies that, in fact, the, say, number of regressions that you have to do actually decreases with alpha. And that's not the case at the moment that we're going to look at the best subset selection. But take into account that there is an important drawback with respect to forward selection in comparison to best subset selection, and that is that best subset selection, even though you're not going to run all the potential regressions, still best subset selection will generally always give you the best regression that there is among all the potential regressions. But that's not the case for forward selection. And the reason behind that is because of the fact that you could actually miss the best regression, and that is because of the fact that it may be possible that features selected in early stages may be highly correlated with features selected in later stages, and therefore they may not be that interesting anymore to include. This is usually called greediness. Greediness is a very general terminology in machine learning to say that we actually try to make steps quite based just on the next step that we're going to take, and we're not going to take, say, things from the past or also things into the future into account. That's a very general thing that we have actually with machine learning. We will come back to greediness later on at the moment that we, for example, are going to look at regression trees. But you should take into account that at the moment that we are going to look, for example, at forward selection, then it could be possible that in the very first stage, so if alpha is equal to 1, that we're going to include a particular, say, feature. And the reason why we're going to include that particular feature is simply because of the fact that we can only include one particular feature. So we're going to include that particular feature, and then later on, it could be possible that there are two other features that are highly correlated to this feature that we have over here. And we should realize that maybe in later stages, it could be interesting to include those, say, two features, because of the fact that you have the possibility, if alpha becomes larger, you have the possibility to include these two features at a time. And suppose that these two features actually together have a much better predictive power than this one feature that we've over here. We did not include these two features if alpha is small, of course, because of the fact that we didn't have the opportunity, especially if alpha is equal to 1, then we cannot include those two features at the same time. And individually these two features we are going to assume have less predictive power than this, say, first feature that we have over here, but together they might actually have a better predictive power. So therefore, at the moment that alpha becomes larger, we're going to include those features. But take into account then that at that moment in time, it might then not be that interesting anymore to have this feature being included. So therefore, it would have been better to exclude it and to take other features into account. Well, you should realize that that can actually be done using, say, best subset selection, but it cannot be done at the moment that we're going to use forward selection, because that forward selection actually doesn't allow that as an algorithm. Well, an alternative to forward selection, which is even faster, is to fit the residuals only on the next variable to be selected in each stage instead of the whole regression line. That implies that what we're going to do is that, forward selection still actually takes all the regressors into account, all the features into account. So that implies that at the moment that alpha becomes equal to, say, 10, then even though, of course, we don't have to take all the features that we have already included into account in terms of, that we are going to include them again because of the fact that we already assume that they will be included, but we still run a regression, a multivariate regression of, say, 10 different features. Well, instead of that, what we could do as well is that we could, say, like at the moment that we already in alpha equal to 1, for example, then what we can do is that if we do already know the optimal, say, feature that we're going to include, then instead of simply running, in the case of alpha equal to 2, a multivariate regression, is that we could also take the residuals from the first regression, say yi minus xi times beta, with this first feature taken into account. And instead of running a regression of yi on, say, these two features that we have in alpha equal to 2, we're simply going to run a regression of the residual on, say, a potential new feature. And this will become much faster, of course, at the moment that we have a situation in which alpha is already quite large. If we have many features and say alpha becomes equal to 40, for example, well then in the case of forward selection we have to do a multivariate regression with 40 different features, which is of course not that difficult for nowadays computers, but still it's maybe not that fast. In the case of this situation, we only have to do, say, a regression with one particular variable, one particular feature. Well, this method actually has another name, and it's called forward state-wise regression. And even though we're not going to use forward state-wise regression a lot, we should realize that forward state-wise regression has some overlap with the idea of regression trees that we are going to discuss later during this lecture series. Now the question, of course, arises, which of these methods are we going to use? Well, the answer to that is actually we're not going to use any of these methods, because of the fact that we should realize that there are actually methods that are even faster than the methods that we discuss over here, and that are definitely also much better than the methods that we have over here. So that is the next thing that we are going to look at. To understand regularization, take into account that best subset selection can also be written as the following constraint minimization problem. Here we are going to have, of course, the minimization that we have in standard ordinary squares, namely that we're going to minimize the sum of squared residuals, yi minus xi times beta. But in this particular situation, what we are going to have is that we only allow, say, well, alpha of these betas that we have over here to be different from 0. If we here assume that all the features are here included and not just the alpha of the total features. And then what we can do is that we can then use the following restriction with respect to that, namely that only, well, if we sum over all the features, only, say, alpha of those features can have a beta I that is different from 0. Well, we could write this as in a restriction, which is going to be an identity or an equality in this particular situation, where we have simply an is sign over here, but we should take into account that we can also have a minus or equal sign over here. And the reason behind that is because of the fact that it doesn't matter that much, and the reason is because of the fact that take into account that at the moment that this relationship would be in such a way that the sum that we have over here is still strictly smaller than alpha that we have over here, then we can always improve or at least decrease this sum of squared residuals that we have over here by including one additional feature, or having one additional feature for which beta is no longer equal to 0. This is the same as saying that at the moment that we are going to include an additional regressor in a regression, that then always the r squared will go up. And well, here we should realize that always the sum of squared residuals will go down by including a different regression. So this is a minimization problem of the squared residuals over all features, with the restriction that the number of positive features cannot be larger than alpha. And even though not really a norm, sometimes this relationship that we have over here is called the L0 norm, but it's not really a norm because of the fact that it doesn't have all the restrictions that are related to a norm. The restriction says something about how large the features in the total feature set are allowed to be, because of the fact that it says that for different values of alpha, it says something about how many betas can be different from 0. Well, if we understand that ID, then you might say like, well, but then we can also think of other, say, restrictions that we can have, or other norms that we essentially can have. One thing that we could do is that we could also use essentially the same, well, restricted minimization problem, but now instead of having this L0 norm that we had over here, we could also use a so-called L2 norm. So then what we're going to have here, this is exactly the same. We're going to minimize the sum of squared residuals, but now under the restriction that the sum of the beta I squareds must be smaller or equal to alpha for some alpha larger than 0. Well, if we are going to do this thing that we have over here, then we are going to get something which is quite well known in machine learning, and it's called rich regression. Well, we should take into account that in this particular case, well, the first thing that we can say is, first of all, that, like what we had with respect to best subset selection, so this minimization problem that we have over here, we could place here, of course, an equality instead of an inequality, but that actually will not really change the result. So in that sense, whether we have here an inequality or an equality, that actually doesn't matter that much. In addition, that what we can say is that, at the moment that alpha is going to be larger, well, that actually then allows the betas to be larger as well. In this particular situation, betas don't have to be equal to 0, but we should take into account that as long as alpha is relatively small, then we cannot make the betas too large, of course, because of the fact that then at that moment in time, the restriction that we have over here will no longer hold, and therefore, since it actually has to hold, we cannot make the betas too large. So therefore, in a rich regression, coefficients are not restricted to being positive or different from 0, but their size is still restricted. And take into account another thing, and that is that, unlike what we had in the previous slide with respect to best subset selection, that this alpha actually did have a nice interpretation, namely that, it actually says, how many betas that we have over here can be different from 0. Such an interpretation we don't have anymore at the moment that we're going to look at rich regression, because of the fact that this alpha, actually doesn't have any kind of interpretation. It's even more than that, because of the fact that we should realize that, what we actually can choose with respect to alpha, in the original situation, you could only choose alpha to be equal to 1, 2, 3, etc., up till the number of features that we have. But in this case, alpha can be, in a sense, any kind of number, as long as it's going to be positive. And the interpretation that we still have with respect to alpha is that, or the only interpretation that we have with respect to alpha, is that the larger alpha is going to be, the less restrictions that we have with respect to these betas. These betas then can be still quite different from 0. Whereas at the moment that alpha becomes very, very small, then generally the betas will not be equal to 0, but they will not be very large either. The larger we actually make alpha, the more, in fact, the betas that we have over here are going to look like a situation that we would have had if we would have run a, regression with all the different features included. So therefore, rich regression will set the coefficients of the features that do not have a lot of predictive power to numbers close to 0. That's another thing that we should take into account, of course, is that generally we have a lot of different features, and we should take into account that some of those features, they have a lot of predictive power. For those features you would like to set the betas relatively large. Depending, of course, on the value of alpha that we have over here. We would like to set them maybe as large as what we would have had in an unrestricted regression, if we would not have any restriction with respect to this, and just would like to minimize this thing that is over here. But of course, there are also features that do not have that much of predictive power. They would increase the R squared a little bit at the moment that you would include them, but generally it is by not that much. And for those, features that do not have that much of predictive power, of course you don't want to set the betas too high. And the reason behind that is because of the fact that if you actually are going to do that, it will not help you that much by reducing, this criterion function that we have over here, but it will result in the fact that this, say, restriction no longer is going to hold, or at least you have to set other kinds of betas very close to zero if you are going to set the betas of those features quite different from zero. So therefore what you're going to do is that you're going to essentially be a little bit more, or at least this algorithm is going to be a little bit more, well, cautious with, in a sense, setting the betas too high compared to an unrestricted regression, in that sense that it will set at least the regressors or the coefficients of features with not that much of predictive power very close to zero. It's very unlikely that it will be exactly equal to zero, but they will be very close to zero. Note that in this case we can solve the constraint minimization problem by using Lagrange multipliers. And therefore first note that the minimization will never be in an interior point, as I already said. And that's exactly the same as what we already have seen with respect to best subset selection. In a sense, at the moment that this is going to be a strict inequality, well, then we can even always increase some of the betas that we have over here in such a way that we are going to have an equality over here and reduce, in fact, this criterion function that we have over here. So at least as long as alpha is not going to be too large, of course, if alpha is going to be really, really large in such a way that you're going to have, say, the unrestricted regression anyways, well, then there is no problem, of course. But at the moment that the alpha is not too large, well, then it will always be possible to improve, in fact, this relationship that we have over here by increasing some of the betas in such a way that you are going to get an equality rather than an inequality. So therefore we should realize that we can also see this as an constraint minimization problem with actually an equality rather than an inequality. So for that we have Lagrange multipliers, or at least we have the method of Lagrange multipliers. For that we are going to introduce a new function that I denote here by this calligraphic L that we have over here. It's going to be a function of the betas, of course, but apart from that, this lambda that we have over here, where lambda, of course, is what we usually call the Lagrange multiplier. And then what we need to do is that we have to rewrite this sum of squared residuals. Well, suppose that you already know that you can, in matrix notation, you can write it in this format we have over here: y minus x times beta transpose multiplied by y minus x times beta. And then, well, we have to subtract from that. Well, essentially what we have to do is that we have to subtract from that lambda multiplied by, in fact, the rewritten restriction that we have over here. The restriction now has to be equal to 0 on the right hand side, so that implies that I'm going to put this to the left hand side, and I'm going to get the sum of the beta I squared minus alpha is equal to 0, and we can actually rewrite that as alpha minus beta transpose times beta. This thing that we have over here must of course be equal to 0, at least if the restriction is going to hold. So that actually implies that officially, as long as this restriction is going to hold, of course we do already know that then this L function will actually take exactly the same, say, values as this criterion function that we have over here, which implies that by minimizing this thing that we have over here, we also are going to minimize this thing that we have over here. But now we can do that with respect to two different variables, both beta and lambda. Well, it implies that we are going to have first order conditions. First order condition with respect to beta is equal to minus 2 x transpose multiplied by y minus x times beta plus, well, that is this thing, the first order derivative of this thing that we have over here. The other one is a little bit simpler because of the fact that then what we're going to get, well, we get a minus and a minus sign, and we get here, well, this is essentially a beta squared, of course, so we get this 2 over here. So in total we get plus 2 times lambda times beta. That one is to be equal to 0 because of the fact that we have here the first order conditions, and in addition that at the moment that we're going to take the first order condition with respect to lambda, well, lambda only appears over here. After a little bit of rewriting, we'll actually simply get the restriction, namely beta transpose times beta is equal to alpha. The first thing we can do is that we can say a little bit more about the first order condition. First thing that I actually can do is that I can divide the left and right hand side here by -2. Then I get this relationship that we have over here, namely x transpose multiplied by y minus x times beta minus this lambda times beta is equal to 0. Now what I would like to do is that I would like to take the betas together here. So one thing I can do is that I can get rid of the parentheses that we have over here. If I'm going to do that, then I get this thing that we have over here. Then we get, well, x transpose times y minus, well, x transpose times x times beta minus lambda times beta, the thing that we already had, of course. So we simply multiply these things. So x transpose times y minus x transpose times x times this beta that we have over here in order to get to the next step. Well, then what I can do is that I can take these two things together, of course, because they are both multiplied by beta. So if I'm going to do that, and if I also take then, well, then I get parentheses, of course. I get here minus x transpose as x plus, of course, this lambda that is over here, but I can then take them to the other side. So then what I'm going to get is a plus sign in front and this thing over here, as I already said. And then the only thing that I still have to do is to invert the left and the right hand side by this matrix that we have over here, which implies that on the right hand side I simply get beta. I'm going to write that now actually on the left hand side, and now on the right hand side, or originally of course on the left hand side, we have now the inverse of this function that we have over here, x transpose times x plus lambda I inverse, of course, and then we multiply that by x transpose times y. We for a moment are going to look at this relationship that we have over here. Take into account that this is not the solution yet, and the reason behind that is because of the fact that, well, lambda has to be solved as well. So that is a thing that we still have to do. But take into account that this actually already looks a lot like a, say, standard, or the formula that you have with respect to standard regression analysis, because of the fact that you must know already for a long period of time that if you would like to calculate beta for standard ordinary squares, then what we're going to get is x transpose times x, then the inverse, and multiplied by x transpose times y. That is what we usually get for a standard ordinary squares regression. So the only difference that we have now over here is that we have here plus lambda multiplied by I. Well, if we assume that this lambda that is over here is going to be positive, well, then we should take into account that, well, given the fact that this is actually a squared term, so at least along the diagonal, these are going to be positive numbers, and we are going to add additional positive numbers to that along the diagonal. That implies, of course, that one thing that we still have to ask ourselves, of course, is whether this thing that we have over here is invertible or not. That might not be the case, of course, especially if the number of features that we have over here is extremely large. Then it could be possible, of course, that this thing is even not invertible or very difficult to invert. But we should realize that if we are going to have this one that we have over here, then at least at the moment that we add to that something positive along the diagonal, then it is going to be more likely to be invertible compared to this one that we have over here. Usually we have to invert this one only, of course. Well, this one over here might not be invertible, but at the moment that we're going to add to that along the diagonal a, say, lambda to all the elements along the diagonal, which is positive, well, then it makes it more likely to be invertible. We still don't know, of course, whether it's always invertible, but it at least makes it more likely to be invertible. So that implies that even in the case that we would have had here, say, problems with this particular regression, maybe because of the fact that we have included too many features in this regression, in the sense that we get a very high level of multicollinearity, well, then at that moment in time, by adding this term that we have over here, we can admit in fact that this thing becomes uninvertible. So that is actually a quite nice thing, and that was also one of the reasons why people actually started with ridge regression in order to admit multicollinearity. Well, that's essentially a stupid thing. I'm not going to talk too much about that, but at least as a prediction method, ridge regression could be very, very great. But that still implies that one thing we still have to do is to ask ourselves the question, how are we going to solve with respect to lambda in this case? Well, essentially that is quite simple. What we simply have to do is to substitute this beta that we've over here into the second first order condition. So what I have to do is to substitute this into there, and if I'm going to do that, then I'm going to get this relationship that we've over here. Well, this is of course a very difficult relationship, and very, very difficult to actually solve in this case lambda, of course. So what we essentially now have to do is to not have alpha here at the left hand side and lambda here at the right hand side, but what we want to have is just lambda here in the left hand side, and everything else, including of course is alpha at the right hand side. But that is actually not possible in this case. It's impossible in this case to get directly a relationship that gives us a, say, closed form of the lambda that we have over here. So that makes it quite difficult. What we can do is of course to try to calculate this numerically for any kind of situation, and then substitute that back into this equation that we have over here. But that's usually not what we do with respect to ridge regression. And the reason behind that is because of the fact that we should realize that we are actually not that much interested in lambda in the end, because of the fact that lambda of course is a relationship with alpha, and alpha actually doesn't have a really good interpretation for us. However, one thing that we know for sure is that at the moment that we are going to have relatively high values of alpha, then lambda becomes relatively small. Whereas at the moment that, say, alpha is going to be very small, then lambda is going to be large. That's not that difficult to see that that relationship actually holds. And the reason behind that is because of the fact that here actually lambda is in the denominator here at the right hand side. So in order to get say, at the moment that alpha is very, very small, then in order to get this thing very small here at the right hand side, one thing we could of course do is to improve this lambda that we've over here, because then actually the denominator of course becomes larger. That means that this term that we've over here at the right hand side becomes smaller. So therefore one thing that we know for sure, at the moment that we're going to increase alpha, then lambda needs to be decreased, and the other way around, at the moment that alpha is going to be very, very small, then lambda has to be increased, which means that there is a negative relationship between alpha and lambda. But because of the fact that we actually do not have any interpretation with respect to alpha, that implies that instead of setting alpha, what we could have done as well is simply to set lambda that we've over here. Then there is a corresponding alpha, of course, that actually corresponds to this relationship that we've over here. But we should take into account that we are not that much interested in the in getting the alpha correct here anyway. So therefore what we could do is here as well in this particular ridge regression is simply saying like, well, what we're going to do is that we're going to look at this one over here, and instead of first setting alpha and then to try to get lambda, we immediately set lambda by itself. So that implies that we simply are going to do this thing that we have over here instead. Now, strangely enough, unfortunately, even though it's very common in, say, Lagrange multipliers to use a lambda, in fact, for, say, the Lagrange multiplier, you should realize that, unfortunately, in R and in Python, actually, they denote the lambda that we have over here by alpha. So that's an important thing that you have to take into account. At the moment that you're going to go to R or Python, then at the moment that you have to set the alpha parameter, that's actually the lambda parameter that we have over here. So that means that in Python or in R, a high level of lambda means actually that we have a very, say, high level alpha, I'm sorry. That means that we have a very restrictive, say, regression. because of the fact that that corresponds to a very low level of the alpha that we have over here. That means, of course, then a very restricted regression because of the fact that the betas then cannot be too large. Whereas at the moment that we are going to have in Python a, say, very high level, a very low level with respect to alpha, that means a very low level with respect to lambda, that means essentially a very high level of this alpha that we have over here. And that means that we have a very unrestrictive, say, regression over here. So that also helps us in order to think about how we are going to choose the, say, lambda that we have over here, because of the fact that what we can do then in a cross-validation is that we actually start with a very high level of lambda. That means that almost all the coefficients then will be close to zero, because of the fact that then at that moment in time we have a very, very restrictive regression. Well, that's most likely not going to be our, say, best choice of the lambda that we have over here, because of the fact that that is almost like a standard regression with only including a constant. Well, this generally will not give us very low levels with respect to the cross validation risk, but then what we can actually do is that we can then gradually decrease the level of lambda. That implies increasing the value of alpha, and that implies that we are going to, well, have a more or a less and less restrictive regression. And that implies, of course, that the cross-validation risk will actually go down at the moment that we are going to decrease the values of lambda. However, at a particular moment in time, well, we will see that the cross-validation risk will increase again. Well, then we do already know that we have then already found the optimal level of lambda, and that implies essentially that we can stop over there and choose that optimal level of lambda in order to get our potentially best restriction. I would like now to go on with the next topic, and that's the topic of the lasso. What we should realize is that, well, ridge regression was of course based on the so-called L2 norm, but it's not the only norm that we can use in addition to the so-called L0 norm that we had with respect to subsets, best subset selection. We can also use the so-called L1 norm. Then what we're going to get is the following minimization problem. Then what we're going to get is, say, again, the standard minimization problem that we have in ordinary squares, minimizing the sum of squared residuals. But then in addition to that, we are also going to get now a restriction, and that gives us the L1 norm restriction. Namely, we are going to get the, well, sum over the absolute values of beta I rather than the beta I squareds. And now in this case, this must be smaller or equal to alpha for some alpha which is going to be positive. I'll take into account that if we're going to do this, then we get another important regression method in machine learning, and that is the so-called lasso. Well, we should realize that many things that we have already discussed with respect to ridge regression also hold true in the case of lasso, and well, that implies that also here there is a one-to-one negative relationship between the alpha that we have over here and a potential lambda that we're going to have at the moment that we are going to do essentially the solution. If we try to solve this this method that we have over here, this restricted minimization problem that we have over here, there is going to be a negative relationship between the alpha that we have over here and a lambda, which we can see as a Lagrange multiplier over here, and therefore what we typically do that instead of setting alpha, we instead set lambda, which has exactly the same interpretation as what we have seen before. Namely, if lambda is going to be large, then alpha is going to be small, so that means that we have a very restrictive regression, whereas at the moment that, say, lambda is going to be small, then alpha is going to be large, which means that we have a very unrestricted regression. However, take into account that unlike what we had with respect to ridge regression, it is not that simple to actually solve this minimization problem that we have over here. That we can do with, well, some standard methods with respect to linear optimization, but I'm not going to discuss that over here. What we should take into account, however, is that at the moment that we're going to go for lasso, that lasso is actually a little bit different from ridge. And the reason behind that is because of the fact that we should realize that with ridge regression, well, the betas at the moment that alpha is substantially small, then we should realize that the betas will also be quite small, but they will usually not be set exactly equal to 0. For, say, regressors or features that have relatively little predictive power, even for a ridge regression, the betas in that particular situation, they will be different from 0. They will be small, but they will be different from 0. That's not the case at the moment that we're going to look at the lasso. And the reason behind that is because of the fact that this relationship that we have over here cannot be differentiated. At least not at the moment that beta becomes equal to 0. And that implies that we sometimes are going to be in corner solutions, which implies that typically it's going to be the case that a lot of the betas in the lasso will be set exactly equal to 0. And these are typically, of course, the features that do not have a lot of predictive power. I would like now to go on with the next topic, and that's the topic of an alternative ID behind regularization. So far, I have been looking at regularization essentially as a method where we're going to minimize the sum of squared residuals under a, I would say, particular restriction, either an L2 restriction in the case of ridge or an L1 restriction in the case of lasso. However, there's also an alternative way to formulate regularization, and that is to interpret it as a result of a penalty on the loss function. Let's assume that there is some kind of penalty on a loss function, and we're going to denote that by this new beta that is over here. And in general, we can expect that the larger the betas are going to be in absolute values, the larger also is going to be this penalty. And then what we're going to do is that we're going to minimize a so-called squared loss function that I'm going to denote here by capital lambda. Lambda is of course also a function of beta, and it's first of all the sum of squared residuals, but plus this additional penalty term that we have over here. And now there are different choices with respect to this penalty term in terms of a function that we have over here. The first function that we can choose is to have that new beta becomes equal to lambda beta transpose times beta. That will actually give us ridge regression. And we can also have a second choice where new beta is going to be equal to lambda times, well, the sum of the absolute values of the betas, and that will actually give us lasso. So in that sense, we're going to get exactly the same results as what we had before by using this interpretation of, or this ID behind regularization. I have the ID that, the ID that I described is a little bit more intuitive, making it a minimization problem under a particular kind of restriction, because of the fact that then you can relate that, for example, with best subset selection. But this is the way in which is typically described in many machine learning books. I would like to end the discussion with respect to regularization by making some final remarks. And that is especially related to the question of what should we actually use at the moment that we would like to make predictions, at the moment that we would like to make predictions using regression. Then we of course have two methods. We have, on the one hand, we have lasso, and on the other hand we have ridge regression. And the question arises, which of the two we should use in practical situations? Well, you should take into account that actually both methods are very, very good. So in that sense, you could use either of the two methods, or maybe even better, what you could do is to use both of them and to find out which essentially is going to give us the lowest test risk, and choose that one that is going to give us the lowest test risk. That's the best way you can do, but even in the case that you're just going to, well, choose one of the two, maybe because of the fact that you don't have that much of computer power and therefore you don't want to wait too long in order to do both cross-validation with rich regression as well as with lasso, then it doesn't make that much difference if you're going to use either lasso or rich regression. But suppose that you do have to make a particular choice with respect to the lasso or rich, then the question arises, which of the two should you then use? Well, first of all, you should realize that as the lasso has no explicit solution, it is slower than rich regression. Nowadays, a lot of people always say that the lasso actually is also very, very quick, so that is not really a problem. But take still into account that the lasso actually is much lower than rich regression. It could be even a factor like 5 or 10 times slower. So in that sense, well, if really time is your problem or computer power is your problem, then at that moment in time, it might be better to go for rich regression than using the lasso. But take into account that since both of them nowadays are quite fast, and because of the fact that computers are fast as well, maybe this is not that much of a problem any longer. Then the question arises, what about, say, predictive power? Well, that actually depends on the situation, but sometimes, or in many situations, actually rich might give you better prediction results than the lasso. And the reason behind that is because of the fact that it has this flexible L2 norm rather than the a little bit more restrictive L1 norm. And that can be best explained by scrolling back and first of all going to rich regression that we have over here. Take into account that at the moment that we're going to look at rich regression, then actually the nice thing with respect to rich regression is that it can actually take every feature differently into account in terms of its predictive power. It implies that those features that really have an enormous predictive power, well, they will usually be set very, very high in, say, absolute values. So that implies that they might even have almost their beta values that they would have had in an unrestricted case that we have over here if we only minimize this, say, sum of squared residuals. However, of course, there could be also, say, regressors or features, better to say, that essentially are going to have less predictive power. Maybe still they have some predictive power, but it's less than the ones that really have a large predictive power. Well, for these, what rich essentially does is that it's going to give us still beta coefficients that are quite away from zero, but they are going to be simply a little bit smaller. They generally are going to be in absolute values a little bit smaller because of the fact that you don't want to waste too much of the, say, capacity that you have with respect to this restriction that we have over here in a sense of this particular feature, because of the fact that the feature by itself doesn't have that much of predictive power. And then you should realize that, of course, apart from the, say, features that have a lot of predictive power and that have a little bit less predictive power, you have, of course, well, creatively features that have less and less predictive power. And you do, of course, have a couple of them that have almost no predictive power. Well, rich will take those into account as follows, namely the ones that have really, really low levels of predictive power, by setting the betas almost equal to zero. They will never be set exactly equal to zero, but they will be set almost equal to zero. And the reason behind that, of course, is because of the fact that if you set them almost equal to zero, then since the fact that you're going to square them as well, well, will make the cost of them more or less equal to zero. Because if we, for example, have here a 0.0001, if we square it, well, then the costs are more or less equal to zero. So therefore, take into account that even though the beta coefficients will never be exactly equal to zero, there will be some, say, features that have beta coefficients that are very close to zero. And that's because of the fact that they actually don't add that much in terms of, well, making the prediction any better. Well, apart, of course, from rich, we also have lasso. Well, with lasso, it works a little bit different because of the fact that you have this problem that this is actually not differentiable. We will end up in a lot of, I would say, corner solutions. That means that, well, the same actually is true with the features that have a lot of predictive power. They will generally have relatively high betas in absolute values, maybe even almost identical to what we had with respect to the unrestricted minimization that we have over here. That's exactly the same as what we had with respect to ridge regression. However, we should take into account that at the moment that we are going to look at, features that have less predictive power, well, they will generally be set having betas that will be set exactly equal to 0. And that makes essentially a little less flexible in terms of being able to make predictions. Ridge is very, very flexible because of the fact that it can have a whole range of, different, values of beta that we have over here, in the sense that it could be really large up to really small, whereas, well, with respect to lasso, you have much more the question between, well, is it, different from 0, or is it exactly equal to 0? Of course, if it's different from 0, then you still can have different values with respect to the betas, based also here on, in fact, how large the predictive power is. But you should take into account that essentially a lot of the betas will be set exactly equal to 0. And that makes it a little bit less flexible. And that also implies that in many situations, ridge is able to get, in that sense, a little bit better performance in terms of predictive power. Now the question, of course, arises, is there also something good to say about lasso? Well, there is a very important thing which is good to say about lasso, and that is the interpretation. What you should realize is that at the moment that we're going to look at ridge, then it's a little bit complex to interpret essentially the prediction, because of the fact that, well, if you have many features, all the features will actually have betas that are different from 0. And it's a little bit difficult to say whether these, betas are different from 0 because of the fact that there is a lot of predictive power, or because of the fact that, well, they would have been even much higher in the case that we would have been in the unrestricted case. So in the unrestricted case that we have over here, or whether, well, they are just relatively small over here. So that is a problem that we have with respect to ridge regression. That's relatively difficult to interpret the beta coefficients, and also to interpret them in relationship to the, predictive power of the axis that we have over here. However, with respect to the lasso, it is clear that many, of the beta coefficients that we have over here are going to be equal to 0. That implies, of course, that we do know that the corresponding feature doesn't have a lot of predictive power. And that implies that we can actually see which of the features that we are going to use for the prediction in the end, because of the fact that all the betas that are going to be set equal to 0, so all the features that have betas set equal to 0, they will not, contribute at all to the final prediction. And that helps us a lot with respect to interpretation. So therefore, if interpretation is an important thing, we should realize that then at that moment in time, it might be better to use lasso than ridge. But take also into account that generally in machine learning, interpretation is not that important. However, these days there is a whole literature as well as of econometrics, where we actually use machine learning. Their interpretation becomes more important. So therefore, in econometrics, it is actually the case that the lasso is much more popular than ridge regression. Well, then finally, I would like to say something about ridge and lasso at the same time. So even if you would like to do both ridge and lasso, and you're not asking yourself the question whether you have to make a choice between ridge and lasso, then we should take into account that ridge and lasso both have the problem that they're subject to the size of the features. That's a thing that you might already know. At the moment that we, for example, are going to multiply a particular variable, or maybe better to say a particular feature, then we do already know that the coefficient will actually be reduced by a factor of 10. That's probably something that you already know. For example, at the moment that we are going to run a regression, and we are going to, for example, look at the relationship between, well, the house price on the one hand, and we're going to look at how it is going to be affected by the size in, say, square meters or square feet, then we should realize that, well, what we could do is that we could include, say, square feet by itself, but we could also include, of course, squared feet squared. And the reason behind that is because of the fact that you might want to take into account a nonlinear relationship. Well, if you would like to really do it well, then you want to also include, say, squared feet to the power 3 and squared feet to the power 4. But we do already know that if you especially are going to do the last one, taking into account that, say, well, a normal size of a flat is around 600 squared feet, that if we're going to, well, take the square of it, then we already get quite a high number. But if we especially are going to take the fourth power of it, then we get an enormous number, of course. And that implies that at that moment in time, the coefficients that we're going to get are going to be really, really small. Not because of the fact that, say, squared feet or squared feet to the power 4 doesn't have any impact, but simply because of the fact that the number by itself is already quite large. So even if it indicates that we're going to multiply it by a very, very tiny coefficient, we should realize that it then is going to have an enormous impact. So therefore what we typically do at the moment that we would like to report this is that we're going to not take the, for example, fourth power into account, but we're going to divide it by, say, a number, say, for example, by 10,000 or 100,000, such that we're not going to, if we would like to report it, we're not going to get a lot of zeros first, and then, like, after the 5th or 6th or 7th digit after the comma, we get our, say, first digit different from 0. So therefore what we then typically do is that we divide it by, say, that the squared feet to the power 4 by a number in such a way that it's easier to get interpretable results. Well, take into account that this is actually also important at the moment that we're going to look at the lasso. And the reason behind that is because of the fact that also here, if we're going to multiply a particular feature by 10, then the coefficient is going to be reduced by a factor 10 as well. But what does that mean in terms of, for example, at the moment that we're going to look at the lasso? Well, at the moment that we are going to reduce, in fact, the beta coefficients, well, then at that moment in time, for the, say, same predictive power that we are going to get for that particular coefficient or that particular feature, the likelihood that it's going to be included is going to increase because of the fact that the costs become lower, simply by the fact that we can essentially get the same predictive power by a lower beta coefficient that we've over here. And that's, of course, I would say bad. And the reason behind that is because of the fact that then if I would like to include a particular feature by lasso, I want that lasso is going to include that particular feature. The only thing that I have to do is to make that feature very, very large. I could just multiply that particular feature by an extreme amount, and then I'm for sure that it's going to be included because of the fact that, say, the corresponding beta coefficient will be small anyways. That's not a good thing, of course, because of the fact that we should realize that we don't want our, say, final prediction be determined by, in a sense, the size of the feature. So therefore, what we typically then are going to do is that we're going to do a normalization. It implies that what we then typically do is that we are going to, well, first normalize the data, or at least the data of, say, the features which are going to be continuous. And it implies that we first of all are going to subtract the mean and divide the result by the standard deviation. We are going to do that before we do actually a rich regression or the lasso. I would like now to go on with a simulation example regarding rich and lasso regression. And in that sense, we are coming back to the simulation example that we have already seen before, but now I'm going to look at a slide extension. Still what we have is that we have here at the left hand side yi, and on the right hand side we have g star xi, and plus this ui that we have over here, where we still are going to assume that ui is normally distributed with a mean equal to 0 and a variance equal to 0.25. That means that the standard error is equal to 0.5. In addition to that, even though not written here at this particular slide, we are still going to assume that this xi is uniformly distributed between -1 and 2. Then the question arises, what about g star x? Well, g star x is now equal to -half x squared plus 3x plus the sinus of 4x plus 2, in the case that x is strictly larger than 0. That's the thing that we already had, so in that sense there is no difference from what we have seen before. But now I'm also going to assume that g star x is going to be equal to the sinus of 16 times x at the moment that x is smaller or equal to 0. So this makes it a little different, and we will see that that makes it a little difficult to predict this g star x that we have over here, simply because of the fact that we have here the problem that this is a very high high frequency sinus that is very difficult to predict. In addition to that, we also have here exactly at 0 we have a problem of discontinuity of this particular function. Then what we're going to do is that we're going to use a polynomial up to the order 50. So that implies that I'm going to include x, I'm going to include x squared, x to the power 3, even up to x to the power 50. And I'm going to interrelate this polynomial with dummy variables for xi smaller or equal to 0. So I'm going to have a dummy variable for which indicates that xi is smaller than 0, smaller or equal to 0. Interrelated to this 50 dummies that we have over here, we have another dummy variable for xi larger than 0, and we have a dummy variable xi larger than 1. Take into account that that implies that we have here 3 different dummy variables multiplied by the polynomial of 50. That gives us 150 different regressors, and our sample size is still equal to 100. So take into account that such a regression would be impossible for standard regression analysis due to perfect multicollinearity, because of the fact that it's never possible to include more regressors than your sample size in a standard regression. But take into account that due to the regularization, Rich and Lasso do not actually have directly a problem with respect to that. Then what we are going to see is that the Rich has then a test risk equal to 0.44, and Lasso has a test risk equal to 0.4527. Take into account that if I would have done nearest neighbors in this particular case, I would not have done as good, because of the fact that at that moment in time I would have had a test risk equal to 0.4, roughly 0.49. So we see here that actually Rich does a little better, at least, than the Lasso. In order to see that, let's look here at our, say, figure that we have over here. This is a figure that looks a lot like the figures that we have already seen before. First of all, we have here on the x-axis different values of x. On the y-axis, we have either the outcomes with respect to these blue dots that we have over here, so the simulated data points, or it's going to be the outcome with respect to gx. And what we see here is that again we have 100 different data points, and again the best predictor is this orange curve that we have over here. And we should take into account that again, if we would like to do as good as possible, then we should use this orange curve over here. Well, unfortunately, that one is assumed to be unknown, so therefore we could do that only by using a prediction method based on the data that you have. And one thing that we could, of course, do is to use the prediction method of nearest neighbors. If we're going to do nearest neighbors, then we are going to see that nearest neighbors does generally quite well, but not so well in the most difficult parts. This high frequency sinus that we have over here is a little difficult to predict. Well, generally we will see also for the other methods, and also we have a little bit of a problem over here in this discontinuity. This area over here is much better, of course, but we should take into account that the biggest problems, of course, with respect to nearest neighbors is over here. If you're going to use Lasso, then we do see that Lasso actually does quite well over here, not so well actually over here. It misses somewhat this area that we have over here, but still, as we have seen, it does a little better than what we had with respect to nearest neighbors. And then finally, ridge regression, that one well also misses this area over here, but also this is quite well predicted. This area also is quite well predicted. Also here, this part, as I already said, is missed, but this area actually goes a little better with respect to ridge regression compared to both lasso as well as nearest neighbors.